Today I'm going to talk about machine learning for solid-state batteries, and in particular I want to talk about what are some of the progress and what are some of the hype that has been surrounding this very specific topic of machine learning for battery design. Okay, so given that this is mostly a battery symposium, and I thought I would first introduce a little bit what machine learning is for those of you in the audience who are not that familiar. So machine learning is basically the scientific study of algorithms and statistical models that allow a computer to perform a specific task without giving it explicit instructions, and instead it relies on patterns and inference. Okay, so this is a very basic outline of what a machine learning model is, right? For supervised machine learning models, essentially what you do is that you give it some set of inputs and a set of known outputs. So in other words, that's your training data. And what you hope is that by training the model, the machine learning model will learn the relationship between your input and output. Okay? So for material scientists like us, the input is typically some structure or composition, or maybe some features based on the structure or composition. Okay, so things like the electronegativity of elements or that sort of thing. And the output is typically a property that you are interested in. Okay, so it can be things like ionic conductivity, voltages, energies, and so on and so forth. Now, obviously, machine learning has gotten a lot of hype in recent years. So, and this is with good reason, right? Because a lot of the technological advances that we are seeing currently and in the future, they are based on machine learning algorithms, right? So, for instance, if you are going to build a self-driving car, the one thing that you need is a machine learning algorithm that can detect the environment around it and make decisions based on what it detects, right? So that is powered by ML algorithm. Even very simple things like you go into your Netflix queue and Netflix is recommending you something to watch next. That is also a machine learning algorithm. But machine learning itself is not new, right? So we have been getting weather forecasts for the longest time, and weather forecasting in itself is also a machine learning algorithm, okay? Now, so it is no surprise that a lot of people have been trying to apply machine learning to design solid-state batteries, right? And here I show you a sample of the machine learning literature for solid-state batteries, right? And just not to offend people, I have deliberately anonymized the quotes, okay? So these are basically just extractions based on a Google search of machine learning solid-state batteries, right? And you can see that these are some of the results. For example, this first quote from the abstract says the predictions of this model done on 145 compounds are consistent with the lithium phonon band center, okay? There's also this other analysis that says that, well, our analysis correctly iterates the importance of things such as anion polarizability, but they also found that hopping distance and channel width also influence ionic conductivity, right? Then there's this yet another example where it says that the ML guided search is about 2.7 times more likely to find lithium superionic conductors, okay? Now, what you notice from this selection of literature is that there are major problems with the way machine learning algorithms are being applied in solid-state batteries, right? So for example, just to take the first kind of work, obviously 145 compounds, this is nowhere near enough data for most machine learning algorithms to make sense, right? You don't have any confidence in the results of your machine learning model trained on 145 data points, okay? The second type of problem is sometimes from your machine learning algorithm, you do get insights, but the insights are already somewhat obvious, right? I'm sure those of you who work in the solid-state battery community, it doesn't take a machine learning algorithm to tell you that channel width is going to affect your ionic conductivity, right? And of course, the last one says that, well, I can do things 2.7 times faster. Well, that's not hardly a big advancement, right? 2.7 times faster, and this is based on comparison to a random search. And let's put it this way, if we are doing a lithium-ion battery material search, we are not going to do it randomly, okay? So today what I want to show you is basically what kind of machine learning approaches work and what kind would not, okay? So in general, these are the type of properties that we as a community are interested in for designing an all-solid-state battery, right? And here I'm really focusing on things like either the cathode or the electrolyte, all right? So when designing either a cathode or solid electrolyte, we want to know, for instance, the phase stability of a material. If we are designing a cathode, we want to know its voltage, okay, via computations. If we are designing a solid electrolyte, we want to know its electrochemical stability, right? In other words, what kind of voltage window it will be stable against, right? Ionic conductivity is, of course, important in any part of the cathode, any part of the battery, okay? So the requirements are a lot more stringent in the solid electrolyte compared to the cathode, but even in the cathode, you do want to have relatively fast ionic conductivity. And you have things like electronic conductivity. For electrolyte, you want it to be an insulator. For cathode, ideally, you want it to be an electric conductor. And finally, you also have some mechanical considerations like, well, is the solid electrolyte hard enough to withstand daily use, right? Now, it turns out that we can compute most of these properties today using density functional theory calculations, right? So for instance, things like phase stability, voltage, and electrochemical stability, all you need is a value of the energy, and after you do some analysis, you basically can make a predictions of all these properties. Ionic conductivity is a bit harder, okay? You have to do what's called a nudge elastic band calculations, but essentially it's still a computation of the energy. You can also do molecular dynamics, right? So then you basically extract out the mean square displacement of your ions, and that gives you your ionic conductivity. Now, electronic conductivity is the only thing in this list that is not directly related to just the energy, okay? So this is related to the band gap of the material, which you can get with a DFT calculation, okay? And of course, mechanical properties, you can get it from derivatives of your energy, right? All right, so let's say hypothetically, we want to be able to predict all these properties, and in fact, we actually only need two things to basically to be predicted, right? One is the energy, or derivatives of the energy, and the other thing we need to predict is basically an electronic structure, right? Now, there are two strategies to using machine learning for battery design, right? So the first one is what I call direct structure to property prediction. So in other words, you do exactly what the machine learning model is going is designed to do. You give it a set of inputs, and you just use your direct property as your output target, okay? Now, there is a second way in which you can use machine learning to design batteries, and that is a slightly more indirect approach, which is you use a machine learning model to basically take an input, which is your structure and composition, and what you predict is basically the potential energy surface. In other words, just the energies and forces on the atoms. And then after some simulation or analysis, you can then derive your material property. So things like your ionic conductivity, okay? Now, I'm going to talk very briefly about strategy 1, and I'm going to talk a lot more about strategy number 2, okay? Now, in some instances, strategy 1 is your only option, okay? So there are certain properties which are not directly related to the energy, such as your band gap. Then you basically have to use strategy 1 to basically do the simulation, okay? To do the prediction. So this is a list of predictions that is made by a type of machine learning model known as a graph neural network, okay? And it turns out that graph neural networks are actually a very good architecture for doing material science predictions, right? Because this is a very natural representation for materials. You can think of the atoms as basically the nodes in the graph, and your bonds between atoms as the edges in the graph. And by using what I call graph convolution or message passing to move information in between the bonds and atoms, you can basically create a machine learning model based on that graph representation of materials. Okay, so these are some predictions that are the mean absolute error of various properties based on materials that are in the materials project database. Okay, and the specifics of the different models are not that important, but by and large today we can predict the formation energy of a compound using a graph neural network based approach to within about 30 milli-electron volt or so. We can predict the band gap of a material to within about 0.33 eV or so, and we can even predict things like the bulk modulus, shear modulus, and metal, and also do a classification of whether a material is likely to be a metal or insulator. Okay, and all these are based on direct structure to property training. In other words, we are using things like the band gap, the formation energy, or the bulk modulus as the target for the machine learning algorithm. Now, and this performance is actually fairly impressive for a machine learning algorithm. Okay, so for predicting the formation energy, if we are able to do it within 30 milli-electron volt or so, we are already well within the limit that Wenhao San has found, that you can actually find about 80% of the structures in the ICSD have energy above the ground state of within about 100 MeV per atom or so. So with a 28 MeV per atom error, we are already able to make a very good determination whether a material is likely to be stable or not stable. Okay? So for things like phase stability prediction, we today already have the machine learning algorithms that can predict energies to sufficient accuracy for us to make that prediction. Okay? However, there are properties which structure to property prediction is definitely not a good idea. Okay? And here I show you the example of ionic conductivity. Right? Now, for those of us who work on lithium superionic conductors, we have known for the longest time that the ionic conductivity does not behave very well with changes in composition or structure, right? So for example, this on the left here, I show you the argyrodite. Just by changing the sulfur to chlorine ratio and with a small change in my lithium content, I can already change my ionic conductivity of the argyrodite by about 2 orders of magnitude, okay? Similarly, in LLZO, okay, we have heard a lot about LLZO this morning. People have known for the longest time, cubic versus tetragonal, you already have a huge difference in ionic conductivity. You just dope a little bit of a different element into LLZO, you get 2 orders of magnitude change in the ionic conductivity, okay? Na3PS4 is another example in the sodium space, okay? Just the difference between the cubic and tetragonal structure, again, is a few orders of magnitude difference in ionic conductivity, okay? And the common theme here is that ionic conductivity is a property that exhibits a very sudden change with a very small change in structure and composition space. In other words, your input is changing very small, but your output is changing in a very unpredictably large manner, okay? And this kind of prediction is extremely bad for machine learning algorithms to learn, okay? In general, most machine learning algorithms, they function best when your input and output actually changes somewhat smoothly with one another, okay? So this is the reason why whenever I see a paper that claims to predict ionic conductivity using machine learning algorithms, I almost, as a rule, I will never believe it, okay? Because I don't believe that you can capture a 2 orders of magnitude change with a tiny little bit of doping in any kind of machine learning algorithm, okay? Now, this brings me to the second type of approach, which is basically instead of directly going from structure to property, we can do the intermediate step, which is we can predict the energies and forces, which is our potential energy surface, and use that to actually simulate the property that we are interested in, okay? So this kind of machine learning algorithms, they have a specific name, and that is basically called machine learning interatomic potentials. So the way that machine learning interatomic potentials work is that you take the local environment around each atom. You express it in terms of some local environment fingerprint. There are many, many formalisms that have been developed over the past 10 years or so. And then you use a machine learning algorithm to map that local environment descriptor to basically your energies and the forces within your system, okay? And again, for machine learning models, it can be anywhere from just a simple linear regression to a neural network. And all those are fairly well established, right? And the nice thing about machine learning interatomic potentials is that they tend to outperform your traditional interatomic potentials by fairly substantial margins, okay? So this is a comparison of the root mean square error in the energies and forces of machine learning interatomic potentials versus traditional interatomic potentials. And the darker the color, the lower the mean absolute error, or rather the RMSE. And you can see that in general, it doesn't matter which formalism you choose. All of them have much lower errors compared to your traditional embedded atom method or modified embedded atom method, okay? Now, the nice thing about machine learning interatomic potentials is not really just about the low errors, right? It is also that interatomic potential fitting today can now be standardized and automated. So whereas in the past, getting a grad student to fit a good, say, EAM or mean potential for some simple alloy is going to take him the better part of his PhD, today you can essentially fit an interatomic potential, which is more accurate than the EAM, to any system that you're interested in within a few weeks or so, okay? And this can be done in a semi-automated and standardized way, okay? So you can actually create recipes for building machine learning interatomic potentials, right? So what does this have to do with solid electrolytes, okay? So it turns out that the general way in which we have been using computations to study solid electrolytes have some severe limitations, right? So we have used ab initio molecular dynamics to study solid electrolytes for quite some time now. And here I show you two examples, which is the Li7P3S11, which is actually a work from my group back in 2016. Here on the right is basically another ab initio molecular dynamics work done on Li3YCl6, which is from the group of Yifei Mo in University of Maryland. And what you will see is that the predictions from your AIMD simulation for the room temperature ionic conductivity has a very large error when compared to your experimental room temperature ionic conductivity, right? So for example, for Li7P3S11, this work actually predicted an ionic conductivity of 57 millisiemens per centimeter. And we know that this compound, no one has ever measured the ionic conductivity more than, say, 70 millisiemens per centimeter, right? Similarly, for Li3YCl6, the AIMD predicted ionic conductivity is 40 millisiemens per centimeter, and the experimental ionic conductivity is only like 0.72 millisiemens per centimeter. Now, there's a good reason for this kind of big errors, right? And the reason is because, first of all, we are using ab initio techniques, so the cell sizes tend to be very small. That's one reason. We also have to do simulations at fairly high temperatures to get enough diffusion statistics, okay? So what happens is that all these simulations are performed at, say, 600K to 800K to 1000K, and then we just draw a straight line down in our Arrhenius curve and then say that's the room temperature ionic conductivity, okay? And finally, the simulation timescales are also fairly short, right? So tens of picoseconds to maybe hundreds of picoseconds, and that's it, right? Now, once we are able to fit machine learning interatomic potential, we can essentially get simulations that are almost to AIMD level of accuracy, but we are now able to do simulations at much larger simulation sizes, at low temperatures, and at much longer timescales, okay? So just to show you, this is a nanosecond machine learning interatomic potential simulation. We did it with MPT ensemble, and we did it from 300K to about 800K for these three different superionic conductors, all right? And this is the Arrhenius plot that we get as a result of those simulations. So what you see is that, first of all, our predicted room temperature ionic conductivities are now much more consistent with what you get from your experiments, right? So in all three cases, for this sulfide, oxide, and chloride, we all get very, very good agreement with experiments. The other thing that you will notice is that there is this kink in the Arrhenius plot, right? So it's no longer just a straight line. And we find that this transition in the different Arrhenius regimes occurs at about 400 to 525 Kelvin for all the three lithium superionic conductors. And it turns out that this is something that people have observed in experiments, right? So this is a work by Sockers back in 2011 on the LLTO superionic conductor. And you see that they also observed the very same kink in the ionic conductivity at around 400 to 500 Kelvin, right? Now, with these simulations, we can actually determine the reason for this kink in the ionic conductivity. And it turns out that when you go from the low temperature regime to the high temperature regime, you actually can go from either a two-dimensional to a three-dimensional diffusive regime, or you can also activate additional diffusion pathways at that high temperature. And this is the reason why the slope at this high temperature region is actually much smaller than the slope at this low temperature region, okay? So in other words, we are now for the first time able to basically do simulations that predict ionic conductivities that are reasonably close to what experimentalists have been measuring, okay? Now, of course, we can go beyond that, right? So this is a more recent work that we have done in collaboration with the group of Xiaoqing Pan in UC Irvine, where we basically look at this modified version of the LLTO superionic conductor, which is lithium, strontium, tantalum, zirconium oxide. So this was first proposed by John Goodenough, okay? And the reason why we look at this compound is because it does not contain titanium. So in terms of electrochemical stability, it's actually much better. And it is also known that this LSTZ superionic conductor actually does not suffer from the same low grain boundary conductivity that is observed in LTO, okay? Now, with machine learning interatomic potentials, we can actually do proper grain boundary simulations now and try to determine what happens at the grain boundaries of this LSTZ material. And basically, we can derive insights such as, for example, compared to LTO, we do not actually see lithium depletion at the grain boundaries, okay? And because the reason why there's no lithium depletion at the grain boundaries is because you actually have strontium vacancies that are formed instead of lithium vacancies, okay? And the net result of this is basically that you have grain boundary conductivities that are fairly similar to what you get in the bulk. And this is the reason why LSTZ actually has a total ionic conductivity that is much better than, say, LLTO, okay? Now, from this morning's session, you know that high entropy solid electrolytes are now all the rage for suddenly, okay? And we have also looked at high entropy, or what we call a complex concentrated version of LSTZ, this LSTNZS, which contains tantalum, niobium, zirconium, tin, and as well as lithium and strontium in the lithium side, as well as this LSTNZH, which contains hafnium. The reason why we wanted to look at this set of compounds is because they are, our experimental collaborators, the group of Professor Jian Luo at UCSD, actually found these materials to have about a 60% improved ionic conductivity compared to your LLTO, the standard LSTZ material. Now, we were also able to get fairly good agreement in our simulations compared to this material, the measured ionic conductivities of these two materials. But what I want to show you here is really not about the computational predictions, but really about the process in which we had to go through to get our machine learning interatomic potential for this system, right? So we use an approach called active learning, which you basically do simulations, you have additional data, and then you put it back in, and then you redo your refit your machine learning interatomic potential again. And because this is such a complex system, so this is 7 to 8 elements, we actually took more than 100 active learning cycles to basically fit the potential for this system. So while machine learning interatomic potentials are great, they do have some limitations, which is that when your chemical complexity becomes too high, you actually have difficulty fitting a potential that can cover that chemical complexity, okay? Now, this is where the graph architecture comes in again. So recently, my group has developed what we call the materials tree-body graph network, which is a new architecture for developing a machine learning interatomic potential where we incorporate traditional tree-body interactions into a graph neural network-based architecture, okay? Now, given the same training data, we can show that basically we get roughly the same errors in energies and forces compared to your other machine learning interatomic potentials. But the key strength of this M3GNet architecture is that for the first time, we can actually fit interatomic potential for the entire periodic table, okay? So what we have done is to basically go to the materials project, we have, which has performed about 100,000 DFT structure relaxations since 2012. And that gives us about 100,000 energies, about 10 million forces, and about 1 million stresses. And we throw all this in as training data to build one gigantic universal potential for the entire periodic table, okay? And this is what we call basically an AlphaFold for material science, because we can actually now predict structure without actually having to rely on ab initio calculations, okay? So these are just some performance benchmarks. We can predict energies to within about 33 MeV per atom or so. The force errors is also very low. We do slightly worse on the stresses, but in general, that's still reasonable. But the main value of M3GNet is that today, now we are able to do DFT-free predictions of structural relaxations, energies, and stability. So if you remember, most of the properties that we are interested in for a battery, they are all related to the energy somewhat, right? So we can actually get the energy to within about 15 to 50 MeV per atom of the ground state, okay? So this is already quite reasonable. We can already make good structure stability predictions from it. We can predict the volume to within about less than 1% error, okay? So again, this is important, right? Because once we actually can get the structural parameters, our ionic conductivity predictions tends to be much better, okay? So this just shows you the distribution of the E above how predicted by M3GNet versus DFT. And what you see is that generally the predictions have the same distribution, okay? These are just some additional benchmarks for those of you in the computational space. But once we are able to build interatomic potential, we are now able to perform dynamic simulations as well. So we can go beyond just simple energy predictions, right? So we can, for example, simulate the phonon dot center. And again, this is a prediction from our M3GNet potential, and against basically DFT calculations of the phonon dot center. And again, you can see that the accuracy is extremely good. You can simulate the bulk modulus directly, and again, the accuracy is fairly in line with what you get from DFT. You can even do things like simulate the ionic conductivity of a solid electrolyte just using the universal potential itself, okay? And here I show you the example of Li3YCl6, and you can see that the predicted ionic conductivity at room temperature is actually in fairly good agreement, okay? All right, so for those of you who are interested in trying this out, all these code are actually available on GitHub, and you can basically, you have the original TensorFlow implementation, which is fully functional. It does not have GPU support. We have actually collaborated with Intel to develop this library called Materials Graph Library, MEGGL. This is completely rewritten in PyTorch, and the implementation is already completely done, and I will actually highly recommend that you use this package instead. Now, since the publication of M3GNet, actually a lot of people have become quite interested in it. So I'm, of course, the developer of PyMagen. I've integrated M3GNet into PyMagen itself. You can use it for relaxations. You can also, there are also commercial software providers such as the Amsterdam Modeling Suite, as well as Advanced Soft, who have developed interfaces to this universal potential, okay? Now, we are also building this database, which is a completely new database that is purely based on machine learning-based predictions called Metaverse.ai. We intend for this to be a complement to the materials project. So materials project will always be focused on known structures mostly, as well as DFT predicted properties. So this is basically the gold standard in accuracy still. But what we hope to achieve with Metaverse.ai is to really greatly expand the space of structures that we as a community can explore, right? So this is a pure machine learning-based predicted property database, and it is going to be continuously updated, and our idea is really to go beyond just the 100K or so crystal structures in the materials project to 1 billion structures or more, okay? Now, the website is already live. If you go in and you type, for example, Li3YCl6, you can actually pull up some information on the different predicted structures that Li3YCl6 can take. We actually make predictions of things like the formation energies, the band gap, not just the PBE band gap, but also things like the experimental band gap, because we actually have a model that we believe can predict the experimental band gap pretty well. We have predictions of things like the Bout and shear modulus, and we are also going to add in some thermal properties like the phonon dot center, the heat capacities, the thermal conductivity, and so on and so forth, okay? All right. Now, where can you use M3GNet? Essentially, anywhere that you use DFT for the potential energy surface, but you do not actually require absolute DFT accuracy, right? So, classic example, right? We have all seen this funnel before. We always do our high throughput DFT calculation, then we funnel it down, and then finally we ask our experimental colleagues to try to synthesize some of the materials that we predict, right? Now, with M3GNet, basically what we can do is that we can expand the top part of this funnel, right? We don't actually have to just start from DFT. We can start from M3GNet to do a much bigger space of materials, and then we funnel it down to do DFT calculations, right? This is more for the computational material scientists, so I'm actually not going to talk about this, but essentially you can also generate structures for fitting machine learning interatomic potentials, okay? So just to give you some examples of how we have been using M3GNet to study lithium superionic conductors, we can use it to predict things like the ionic conductivity to a fairly good accuracy. We can also predict things like the electrochemical window, okay? Remember, the electrochemical window is essentially related to the energy of the compound relative to other compounds in the same space. And what we find is that this is, on the left here is basically what you get with DFT calculations, and what you get on the right is basically what you get with our M3GNet universal potential. And you essentially can see almost no difference between the two, okay? So in other words, we can use it to screen for compounds with high electrochemical window or low electrochemical window, depending on what you are looking for, okay? All right. This slide basically shows you how we have been using it to search for good ionic conductors, okay? And these are simulations that are performed using M3GNet. And what you see is that all the known lithium superionic conductors, things like your LGPS, your LTO, your LZO, they all sit within this region of space, right? And this region of space is essentially the compounds with low activation barriers for diffusion, as well as a high initial diffusion at fairly low temperatures, okay? And you can see that we basically can identify all of them, and also there are plenty of compounds within this space that people have not yet explored, okay? All right. I want to conclude. I would say that material science knowledge is even more important, in my opinion, in the age of machine learning, because otherwise machine learning algorithms can actually lead you astray. The first type of machine learning model, where you basically just go from input to property, I would recommend people use it only sparingly and only in instances where your property actually are fairly well behaved with the input, okay? So things like ionic conductivity, where small changes in input can cause large changes in properties, those are generally not good for machine learning algorithms, okay? The second type of machine learning application is basically machine learning interatomic potentials. They are very rigorous and well established by now, okay? So people have already worked on it for 10 years or more. The potential energy surface is actually very well behaved with changes in positions of atoms or the chemistry. It should be the preferred option when your property is actually some function of your potential energy surface, okay? So if you can derive your property from thermodynamic relations with the energy, or you can simulate it directly from dynamic simulations with the MD, you should prefer that approach rather than trying to predict the end property directly from your input, okay? And finally, today we are even able to build potentials that cover basically the entire periodic table. And with that, we can actually explore the entire space of known materials rather than just confining ourselves to one small part of the periodic table, okay? And with that, I just want to acknowledge funding from the Department of Energy, as well as the MERSAC for all the work on the high entropy solid electrolytes, and my collaborators, Jian Luo and Xiaoqing Pan from UCSD and UC Irvine, and also my group members who, of course, did all the work that I'm taking credit for right now. And I'm happy to take any questions.